So in this video we're going to convert rectangular equations into cylindrical equations. So here we have the equation x squared over 9 plus y squared over 9 equals z squared. And this is a double napped circular cone if we were to graph it in 3D. And one of the things that you look for when you're doing these conversions is to see if you can get an x squared plus y squared. If you can, it's always handy because you can immediately replace that with an r squared. So this is one where I would multiply through by 9 as my first move. And I would do that in order to get the x squared plus y squared isolated, which then allows you to immediately replace it with r squared equals 9z squared. And then we could stop here, or we could think about simplifying this by taking the square root of both sides. If we did that, we would get a plus or minus right here. And then we'd have to either justify that if we wanted to make it just plus 3z, we'd have to come up with a justification that we're able to always select an angle that makes the radius representation positive. So that would be an argument that would need to be made if we were going to simplify that further and not have a plus or minus in front of it. In this case, though, I think stopping here is all right, although solving for r is typically what you're trying to do. So here's another one, y equals x squared. So what we want to notice here on y equals x squared is that the z coordinate is missing. So if I think about the xy plane, I just have a parabola in the xy plane. And because we're working in three-dimensional space, the z coordinates missing tells us that we're going to have a parabolic cylinder extruding parallel to the z-axis. So we're going to get parabolas repeating over and over again, infinitely far in that direction and in this direction, and parallel to the z-axis. So to do this one, we're going to recognize that y can be replaced with r sine theta. Again, to convert from rectangular into cylindrical form, I have a rectangular equation. I know that because of the x and the y. I need to get an equation that only has radius, theta, and z in it. Any of these can be missing, but I can't have an x or a y. So in this case, I'm going to replace the y with r sine theta equals, and then x is equal to r cosine theta, so x squared is going to be the square of r cosine theta. So x squared can be replaced with radius squared times the cosine squared of theta. And then to solve this for r, I could simply divide both sides by r times the cosine squared of theta. Try to make that theta a little bit nicer. And then I would divide this side by r cosine squared of theta. And then there's a couple things to realize here. We're in a little bit of a danger zone, because if the cosine squared is equal to 0, we can't divide by it. And if the radius is equal to 0, we can't divide by it. And if I look at my parabolic cylinder here, there will be locations where the radius is equal to 0. So if we do this simplification and we rewrite this as sine of theta over cosine squared of theta by doing radius divided by radius equals 1. Radius divided by radius only equals 1 if r isn't equal to 0. So what we want to ensure, on simplifying this side, we just get radius. What we want to ensure is that we can still get a radius of 0. In other words, we don't lose the fact that the radius is going to be 0 sometimes. We don't want to lose that fact by doing the division by r. And so here I want to notice that this ratio will be equal to 0 when theta is equal to 0. So there is an angle theta for which I will get a radius of 0. So I'm okay with then dividing by the r right here like I did, and not losing the fact that the radius is equal to 0. And we could leave it like this or simplify it by recognizing that this can be rewritten as sine theta over let me do it up here. It gets messy on the bottom. So if I just bring this up, I could rewrite this statement here as sine theta over cosine of theta times 1 over the cosine of theta equals the radius, and then sine over cosine would give me tan theta, and 1 over cosine would give me secant of theta equals r. And the secant of theta is never equal to 0, but the tangent of theta is equal to 0 when theta equals 0. So again, we aren't losing information by having divided by r right here. So anytime you divide by something and that thing can potentially be 0, you need to think through and justify your dividing by that number. So in this particular case, when I look at the cylinder, the radius is equal to 0 sometimes. So we do have to identify that the final simplified statement can still generate, for an appropriate theta, a radius that is 0.